Hi, everyone. Today, we're going to be looking at portfolio optimization using Ensemble stacking approach. So basically, what we'll be using today is an Ensemble regressor, where we'll be trying to perform portfolio prediction to be able to perform the price of the stock market in the future. And for this exercise, we will be using Yahoo Finance data. And then we will when we use that data, we can decide to pick up any tickers, maybe Facebook's ticker, Tesla ticker, or S&P 500, or whichever ticker that we want. And now we'll be able to make a prediction using Ensemble regressor. In order to begin, I would like to share my collab screen where we'll be performing the experiment. And as you can see, in order to save time, I have set up the environment already. The first thing we are going to do is import the relevant libraries. After that, we will download the data, the stock data from Yahoo Finance. And then in order to be able to perform the ensemble regression, we would need to collect different data sets from different tickers and now perform what we call simple moving average on our data set. And eventually we'll build our ensemble regression model. And after that, we can now try to create our portfolio optimization model, which we'll use to predict the future price of the stock in the stock market. We would then apply it to some case whereby we'll pick some tickers from our Yahoo Finance data repository. And then we can move on to evaluate the model performance to see how best it is able to predict in accuracy. And finally, we will check the accuracy, precision, the F1 score, and the recall. In order to start the whole process, I would like to import some basic libraries that we will be requiring in the course of this exercise. And to do that, first I will need to install what we call the Pi portfolio, which is very essential. It contains some of the features that we'll need. So we have Pi portfolio, OPT. Now, this is important because it's a library that contains some of the features that will enable us to be able to predict or be able to forecast the value of the portfolio. So I'll change, I think this is supposed to be O. So let's do this and see. So we have pip install by portfolio. So I have the spelling is the problem. So let's see what happens here. I think we still have an error. So let's do this. All right, Pi portfolio OPT. Now we have been able to download Pi portfolio OPT, and clearly you can see it has a lot of libraries that are stored inside the package, which we'll be using. For instance, we have CVXPy, we have NumPy, Panda, SciPy, and so many other packages that will be relevant for our experiments today. Another thing that we will need to install, this is just mere formality. If you have it installed already, you don't have to repeat it again. So in this case, we say we want to install Y Finance, and then we also want to install Pandas. We also want to install scikit-learn. And this only happens once in the event that you assume that you don't have them all installed previously. You need to run all these installation packages to be able to install every single one of them and the various libraries that are stored and the various modules and dependencies that are stored inside them. Now that we have concluded the installation, we would need to import the libraries from the packages we have installed. So the first thing we want to install is Y Finance. We want to import Y Finance as YF because we'll be using it. We also, of course, we need Pandas, so we have to import Pandas as PD. And then in this case, we'll be importing from sklearn because we had installed sklearn as scikit-learn. We'll be importing the Ensemble framework from sklearn in this case. So we have sklearn assembled, then we import random forest. So here we are using the random forest regressor as our main model framework to be able to perform the portfolio optimization and also be able to test for the quality of prediction that we are going to make. The next thing we have to install is, import is sklearn model selection, because considering the fact that we would need to perform the ensemble stacking approach, we need to select, we need to use that to apply the model selection for the data, for the model we will be using. So over here, we use the train test split, where we're able to split our data set, which we're able to use to split our data set. After that, we have to import the metrics, sklearn metrics, which we can now be able to use to perform what we call the mean square error. So we have import mean square error. In this case, we will be performing what we call the model evaluation to be able to check the performance of our model. So we want the mean square error and not the mean log error. And lastly, as part of the libraries we'll be importing, we have pipe plots or pipe forts, which is a portfolio. And then we are importing expected returns. And also we are importing efficient frontier. And lastly, we are importing the risk models. All right. Now, having successfully imported all of this, so we have sklearn assemble, sklearn.assemble. Then we have import random forest regressor. Now, having successfully imported the packages, we would want to now fetch the data sets that we'll be requiring from Yahoo Finance. So in this case, we have to define a function. So we have define fetch underscore stock underscore data. And then we are using the tickers in this case. We are using the tickers and then the start date and the end date of the stock, which means the open and the close date of when the stock is listed for transaction in the stock market. So we have data equals to yfinance.download. So it means we are only downloading the tickers and then the start date and also the end date. So we have yfinance tickers start equals to start date, start underscore date, and end equals to end underscore date. All right. And it equals to end underscore date. And then we return, we want it to return data for only the adjusted close. So we just want only the adjusted close from that data set to be returned. So we want specifically the start date and the end date, and also the tickers for any particular ticker that we pick. Like I said, either for Facebook, Tesla, or Google, or any other tickers that we are going to pick for this experiment. Now that we have been able to pull out or downloaded our data set, the next thing we want to do is define the function that we'll be able to use to calculate the simple moving average, which we would need to be able to estimate for the assembled approach. So we have define calculate underscore feature. Calculate underscore feature from our data. Remember that our data is being loaded from here. So now we are calculating, we're defining a function to calculate the simple moving average for that data. So we are pulling the data in together, and then we're going to calculate the what do you call it? We'll pull it together and calculate the simple moving average for alpha prediction. And now we have features equals to pandas to data frame, and then we say features. So here now we are defining what the variable type should be. We call it simple moving average, which is equals to data dot rolling data, then window equals to window, right? Then we also want to estimate it based on the mean scale. We don't want it on a daily basis or weekly basis. And then we also want to drop missing values because we don't want data imbalance. We're specifically focusing on a location of this. So then we have its return features. So we define features, so we return the features we have defined. Let's see how this progresses. Now that we have finished defining the function to be able to estimate the simple moving average for the alpha prediction, we would need to now build the ensemble regression model. In order to build the ensemble regression model, we would need to define the training data set and also the test, the training data set into data and also target. So we define, we call this build underscore regression underscore model. So first we pick the target, the data set, the train data set for the data, and then now the target train data set. And having done that, we define the model function, which, like we had described earlier, is a random forest regressor. So we're picking the random forest regressor, and then we have n underscore estimate, n estimator to be equals to 100, and then we have random states. So we are estimating for the states of over 100, and then we have a random state of that estimation to run for about 42 different random states. So we define the model to perform the evaluation in our data set for around 100 estimators, and also be able to perform it for a random state of 42. Then the next thing we want to do is fit our model in order to train that model on a specific or selected data set. We could decide to split this data set in the future, and we define this function. Another way we can do is define this function, split the data set, and use the function data to be able to train the model with the data set after we have split it. So this can be done in two ways. One way is to define the function containing the data parameters. Another way is to split the data set and import it into the model and now train it. So we can, both ways will achieve the same result. But in this case, we choose to define the function that contains the parameter before we eventually proceed into using it. Because we are going to be optimizing portfolio, which we call the portfolio optimization, we are going to be checking about the stock for each particular ticker and see how we can be able to predict future price of the stock for, say, an investor. We'll be defining what we call the portfolio optimization model, which is a modern portfolio theory. And to do that, we simply define a function called optimize underscore portfolio. Now, this portfolio model will simply produce a returns, which is eventually the returns of the particular stock. So first we have the mean, which is equals to the expected value. So we have expected returns, which is the mean. So we have returns dot mean of the historic data, historical. So we have mean historical return on the returns. And the next thing we also have is the sample covariance, which is defined as S. So we have sample covariance defined as S risk model dot sample underscore covariance, and then of the return. So in this case, we estimate the mean of the return, and then we estimate the sample covariance, which is the variance of the return. And the next thing we do is to estimate the efficient frontiers as EF equals to efficient frontiers. of the mean and also the standard deviation, which is S. After which we define also the weight, which is the EF dot max underscore sharp. So we're using the Sharpe formula to be able to estimate the weight of each of the stock that will be optimizing. So, which is why we have to include the weight function for Sharpe. So this is equals to EF dot clean underscore weights. And lastly, we call up the returns of the weight, the clean weighted formula. So we have return clean underscore weight. All right. Now that we have defined a model for optimizing the portfolio, we would now need to apply a use case from the data set that we have been able to pull out. For instance, we had earlier downloaded the Yahoo Finance data, but the Yahoo Finance data contains several types of tickers, and each ticker represents a particular stock for a particular company. So in this case, we are selecting the Apple stock, which is one of the tickers we have downloaded. We're also picking the Microsoft stock, which is also one of the tickers. We're also picking the Google stock, which is also one of the tickers we've downloaded. And lastly, we are picking the Amazon stock, which is also one of the tickers we've downloaded. We just don't want the tickers downloaded. We also want the start date, which we had mentioned earlier on. We are defining a specific start date. For this experiment, we just pick between the 1st of January 2020, and then end date, we want it to be, we can say the end date should be 2021, 1st of January as well. So we can pick 1st of January 2020 to 1st of January 2021. So in this case, now we have successfully picked the tickers. Now that we have defined tickers for all this data, and we have also defined the start date and the end date, we can decide to also fetch the historic data into a particular data frame. So we call that data frame stock underscore data. We call it stock underscore data, not fetch underscore stock. So we call that stock data equals to fetch underscore data. Fetch data. Remember that we had earlier defined the fetch data function, which we said is this. It was earlier defined. So it's going to eventually pick. So what is going to happen here is that we are picking this data set. We're going to pull it out. So we have here, first we have tickers, we have start date, and then we have end date. So what this will do is that it's going to use the function fetch underscore ticker and pull out tickers, start date, and end date from this particular, using this function that we have defined earlier. So it's going to use that and embed it into this very expression and pull out the tickers for Apple, Microsoft, Google, and Amazon, and include both the start date and the end date as well. So if we do that, you can see clearly here that it has downloaded. Okay, I think we have the data frame is not calling. Let's see what happens. Okay. Let's see tickers. We have start date. We have end date. Okay. So now we have successfully downloaded 4 tickers with a start date of January 1st, 2020 and the end date of January 1st, 2021. So since we have successfully downloaded and assigned these tickers, we have fetched them and assigned it into data. If you like, we can even try to view that data set and see what is contained inside or how they are stored. And you can see clearly that we have the ticker date, we have the Apple, we have Amazon, we have Google, and we have Microsoft. So clearly we have been able to successfully download only 4 tickers with a particular ticker date. You see, so we have the dates going from this particular date. If you check it properly, if the shape is around, we can also check the shape of the data set, which is, in this case, we can call it stock. Let's go data dot shape. So if we want to see the number of rows and dimension, you can see it has 253 examples or the record and 4 dimension, which is 4 columns, which is the number of tickers that we have specified in our selection. Having done that successfully, the next thing we will want to do is add some features because we want to make a prediction for the future. So we can decide to add a feature. So here we want to calculate for an instance, if we pick like a 30-day simple moving average. So for instance, if we want the window to be 30, so it means we are picking, we want to predict the price of each of the stock for a future, for 30 days in the future. So in this case, we have a window equals to 30, and then we say features equals to that. So we have features equals to calculate features. Recall that we have also defined calculate features earlier on as a function here. So we have defined it under this simple moving average. Now we want to be able to predict for 30 days in the future the price of the stock. So we have stock data, and then we have the window we had just defined, which is 10. So now we can also pull out our features. We can see what is contained or what is stored inside it, you see. So this has clearly added an extra 30 days. It has extracted an extra 30 days from the list, and now it is assigned on the simple moving average. So this is now, the next thing we want to do now is to be able to prepare a target variable for, like, say, the next day's return. For instance, we want to estimate for the next day's return. We can simply say target equals to stock underscore data. So here, what we are trying to do is estimate the change in the rate of stock by percentage for the next day. So we are shifting, so we have shift -1 because we are picking for the next day. And then also we want to ensure that there are no missing values that are encountered. So we have to assign that in the stock target data set. Having achieved that, we can now ensure that features and target have the same number of samples. So in order to make sure that the features and the numbers, the features data set, which we have seen earlier on, and now the target data set, which if we look at clearly from here, has a different result. It has, so you can see that the shape, when we try to check that up, it has 251. And in order to make sure that they have the same number of samples, we have to make features to be equals to features dot reindex, then target dot index. So what we are trying to do now is re-index our feature data set to make sure it has the same length. The previous length of the feature is not, it's about 221, 224. You can see it here. The shape is 224 with one row or one column, one dimension. But now let's see the shape of the feature. So if we check the shape of the features, it's giving us the same length. You can see that it has the same number of samples, 252, as against 224 that features once had. So this line of code help us to reindex it, to change the number to make sure they are the same. Now, having achieved this identity, we can now decide to split the data set into training data set and test data set. If you recall in the previous example, we had defined a function using the train data set, which we didn't have. So right now, we're going to define the train data set and then use that function we had earlier defined to be able to perform our model evaluation. So in order to do that, we have X underscore train, then we have X underscore test, then we have Y underscore train, and then we have Y underscore test. So this is equals to train underscore test underscore split. So here we are using, because we now have features and target to have the same dimension, to have the same number of samples, we can be able to use them together. If we had just used it without running that previous code there, we would have had a challenge. So in this case, we are given the test data set 25% of the data, and then we are given the rest 75% to the training data set. So we have test data set size to be equals to 0.25, which is 25% of the data. And then we say the random state to be 42. Now, having done that, in order to confirm what we have just done, we can check maybe X underscore train, for instance, S underscore train dot shape. We can see the shape that it now has, 189, which is 75% of 252. You can also check that for the test data set. For instance, you check for the test, you see it's just 63, which is 25% of 252. Now that we have done that, we need to instantiate the simple inputter to fill out missing values. If there are missing values in our data set, we need to instantiate a simple inputter framework to be able to fill out these missing values. So in this case, we say from sklen dot input dot import simple inputter. Okay. And then we say inputter equals to simple inputter, and in this case, we're using the average approach, which is the mean strategy to be able to estimate for missing values if they exist and fill them up. So we're trying to ensure that there are no missing values anywhere. Now that we have successfully done that, we want to use that same inputter framework to now fit and transform our training model. So we say the training model train underscore inputted is equal to inputter dot fit transform. So we have inputter dot fit transform of X training data set. So we are trying now in this case to instantiate all the missing values and fit them all together for our training data set. The next thing we will want to do before we start evaluating our model is transform the data set using the inputter fitted on the training model. So we want to transform also the test data set the same way we have transformed the training data set. So in order to do that, we can simply also use the same approach and say X underscore test underscore inputted is equals to inputter dot fit transform, then X underscore test. So this can make sure that we are using the same type of everything is enjoying the same privilege, both the test data set and also the training data set. Now that we have successfully align them together to make sure they have the same types of the same dimension and every missing values are filled up, we can now proceed to build what we call the ensemble regression model with the inputted data. So we want to build the ensemble regression model with the inputted data. To do that, we can say the model which we had defined previously. If you recall earlier on, we had defined our model in this case, where we had defined a model as the build regression model for the train and for the X train and Y train data sets. So we're going to bring up that model right now. So the model is equals to build underscore regression model for X train underscore inputted because right now we are trying to build a ensemble regression model with the inputted data, then y, train. So when we run this, let's see what it gives to us. Now the model has been built with the inputted data. One next thing we want to do, which is very important, to be able to evaluate the performance of all these whole things we've done. We've splitted our data set, we've built a model, we've created an inputted data set, and then we've tried to build our model around that input data set in order to check the performance of all of the model prediction and the performance of how the model has been able to behave around the data set. If there are no overfitting or underfitting, we will now estimate the model evaluation. And the model evaluation will be estimating the mean square error, the root mean square error, and the mean average error. In order to do this, we would import the mean square error and mean absolute error. Because we don't need the mean absolute error, we just simply retain because initially from our library importation, we have imported what we call the mean square error. So in this case, we can just go ahead and estimate the various errors and see how to estimate them. So let's just have from sklen import mean square error, and also mean absolute error. So we're making prediction, and in the prediction, we are also trying to make sure we estimate to see if there is error in prediction. So we have prediction equals to model.predict. So we are predicting future stock for future adjusted close for the stocks we have selected for Apple, Amazon, Google, and Microsoft. So we say x_test _inputted. So we have now, having performed the prediction, we now want to estimate the mean square error. So mean square error is equals to mean square error on y_test, predictions. And at the end of the day, we want you to print out the results. So we have mean square error, MSE. So we'll do the same thing for the mean absolute root mean square error. So we have RMSE to be equals to mean squared error. So mean squared error. Here we have y_test, predictions. But in this case, we want for the squared, because we are estimating the root mean square error, we make sure the squared procedure is false. If we don't put false, it will be true, and if it's true, it's still estimating the mean square error again, so it's duplicating that operation. So in this case, we have print, and then we say the root mean square error, then we call it RMSE, all right? And lastly, we estimate the mean absolute error, So to estimate the mean absolute error, we have mean absolute error, then we have y_test and prediction. So what we are trying to do now is use our predicted data, and then we are estimating how much deviation does the predicted data and the test data set have from each other. Recall that the predicted data set has not seen the test data set, but the inputted data set, which is in this case created as inputted. But for like can decide to also test the same thing for the train inputted, so that we are sure that it has not seen the test data sets before it moves on with this prediction. So in this case, we can simply just run this, and now also print a statement. So we can simply say mean absolute error, mean absolute error, and then we have MAE. So this is going to give us a significant result that would help us to tell if our predictions is accurate, and if there's a huge deviation between the actual data sets or the actual stock prices and the predicted values for the future. So we are predicting for like a future date. So we are trying to ensure that our prediction is close to the actual data set, so that we're able to use that now to forecast for a portfolio in the future. For the price of a portfolio in the future, we are sure that that prediction will be able to be accurate for an investor to rely on. So clearly, we can look at the mean square error here. It's very small, very, very small. We can clearly see that it is from 0.000. That is a very significant, I won't say insignificant. I will say significant error, but very minimal. You also see the root mean square is 0.029 and the mean absolute error is 0.022. This means that the model prediction gives a very it's a bit accurate. There are not much outliers. The anomalies from the predicted data set is not much and can be delineated or eliminated. Now, having done that, we might also wish to estimate the model classification to check for the accuracy of prediction. We've seen the error between the predicted data set and the test data set. We can decide to check up to see the performance of the model, how we were able to classify its performance in the prediction. And in doing that, we would want to look at how the precision in prediction. We also want to look at the accuracy. We also want to look at the F1 score and also the recall. In order to do this, for the SKLM, we can also be able to pull out significant metrics. So we have SKLM metrics, So we have imports. The first thing we want to import is precision score. So we have precision score. The next thing we have is accuracy. So we have accuracy score, and then we have F1 score. And lastly, we have the recall score. Good. Now that we have imported that, the next thing we want to do is convert predictions to binary classification. So we say binary underscore prediction. So we are converting our predicted data set to binary because now we want to use it to evaluate a different types of classification. So we have prediction. So every data that we predicted will be converted to binary numbers. And then we change the type. So we have as type int. Okay. Then we have binary underscore y underscore test. So we're converting also the test data set to binary. This equals to y underscore test greater than 0. So we have as type, and then we also want it to be integer. The next thing we want to do is now, having defined or converted our binary, our prediction to binary, we can now start estimating the precision with using the weighted average approach, also the accuracy. For the accuracy, we estimate it without the weighted average approach because it does not apply in the case of accuracy. But then for the F1 score, we will use the weighted approach, and also the recall, we will use the weighted approach. So let's go. So we have precision underscore score into the binary underscore y test, and then binary underscore prediction. And then we have average equals to, so in this case, because it's the weighted approach is allowed, we use the weighted in this case. And then we print what we call precision. So we have precision So we have precision, then we say precision. All right, precision. We do the same thing for accuracy. So we have accuracy equals to accuracy score, accuracy underscore score, accuracy score. And this is for binary test, binary underscore y underscore test, comma, binary prediction, binary underscore prediction. But in this case, we would not add an average because it's not average weighted average does not apply for accuracy. So we just leave it as that. Then we simply say print accuracy, then we say accuracy. The next one we want to look for is the F1 score. We just call it F1, which is F1 score. Here we have binary test, binary y test, from binary prediction, binary predictions, binary predictions. This is prediction. No, this should be prediction, not predictions. There'll be predictions. Then, of course, the average, weighted average applied in this case. So we have average equals to weighted. Average equals to weighted. The weighted average applied. Then we can also print it out. So we have F score, and then we call that F1. And lastly, for the whole exercise, the next is called recall. Recall is recall score. Now, recall score is binary underscore y underscore test, and also binary underscore prediction. Binary underscore prediction. Recall as well that average, the weighted average also applies here. So we have weighted. Then as well, we print out a recall. So we have recall score. So we have that to be equals to recall. All right. Now that we have been able to successfully define the evaluation parameter, you can clearly see right here now the precision is a bit high. It's around 64%, and the accuracy is around 14%, which is a bit low. And then we have the F1 score, which is around 58%, and then the recall at 54%. This tells you that the model prediction performed a bit fairly okay. Does not really have high performance metric as expected, but it's kind of like give a good idea of how an advanced ensemble metric will perform. So basically, what can solve challenges like this would be a situation whereby we are able to now use multiple models. Like in this example, we simply use just a single model, which is a random forest regressor. Other approaches would be to include different types of model, like the long short-term memory model, which is LSTM, which is a version of the recurrent neural network. Other times you can decide to use the ARIMA, which is the traditional statistical model, the ARIMA model, and bring multiple models together and be able to perform these type of exercise. That would definitely, number one, further reduce the error, and also increase the precision and accuracy of the model all combined. So if you have any question, feel free to leave it in the comment section, and I'll do the best I can to respond to them. Thank you and have a great day.